In the previous section, we described data flow in FPGA. By the end of this module, you will be able to describe how all code in a single cycle time loop finishes executing within one tick of the FPGA clock. Okay, so let's talk about single cycle time loops. So what happens is LabVIEW will automatically optimize code inside a single cycle time loop. And the way it does this is it removes enabled chain registers from the code that's inside of a single cycle time loop. By doing this, we're going to get better speeds, and it's also going to consume less space on the FPGA. So all code in a single cycle time loop is going to finish executing within one tick of the specified FPGA clock. So that's a huge advantage that we've seen. We can turn a 12-cycle while loop, and by putting it inside a single cycle time loop, we're going to reduce that all the way down to one tick. So you can get some significant speed advantages here. So how do you create a single cycle time loop? So the way you would do this is you would go to your project, you would go to your FPGA target and go to a VI that is on your FPGA target. So you would open that up, go to the block diagram, and you would place down a time loop on the block diagram of your FPGA VI. And then from there, you would just put the code that you want to execute inside that particular single cycle time loop. So this slide shows a comparison again of a while loop versus a single cycle time loop. So if you look at the while loop on the left, the code inside there takes about 5 ticks, and also you add the 2-tick overhead of the while loop, so each iteration is going to be 7 ticks. If we look at the single cycle time loop on the right, we see that all of that code, which looks the same, except that it's inside a single cycle time loop, it's only going to take 1 tick. Okay, so you get some, it's going to be, you're saving 6 ticks by placing it inside a single cycle time loop, and it's going to be much faster. In this slide, let's talk about how a time loop behavior changes based on what target it's on. So if you place a time loop on a FPGA VI, it's going to execute as a single cycle time loop and have the behavior that we just described. And again, you can use this to optimize performance. You're going to have better resource utilization, and also you're going to have much faster speeds. Now, if you use a time loop and you place it on a RT target, for example, it would not execute like a single cycle time loop. It would just execute as a time loop. So one reason that you would want to use a time loop on an RT target is you can specify priorities. You can use it to separate deterministic tasks from non-deterministic tasks. And this is stuff that you can learn about in the LabVIEW Real-Time 1 course, or if you look at LabVIEW Real-Time documentation. Okay, so let's take a look at exercise 6.1. And if you're able to at this point, then go ahead and do this exercise. For now, what I'm going to do is I'm going to demo a solution of this exercise. And in this particular exercise, we're going to compare while loop execution versus single cycle time loop execution and kind of compare benchmarks. Okay, so let's take a look at this exercise solution in LabVIEW. So in this exercise, we have a while loop and single cycle time loop benchmarking, and we're going to benchmark the same code, except one's going to be in a while loop and one's going to be in a single cycle time loop. So let's take a look at this VI. Let's go ahead and jump straight to the block diagram. Okay, so if we take a look at this block diagram, we've got the same code up here, except it's executing in a while loop. And that same code down here is going to execute inside a single cycle time loop. And we're going to do a benchmark. So notice that over here, we've got a tick count. And then at the end of all this, we're going to do another tick count. And we're going to do the same thing down here. So we're basically measuring the time it takes to execute this code and to execute this code. So what's going on? If we look here on the left-hand side, we've got 2 to the 10th power. And we're taking that number, and that's how many times we're executing this while loop. So this while loop is going to execute 2 to the 10th iterations. Okay? If we look down here, we're also going to execute this time loop, or the single cycle time loop, 2 to the 10th iterations. Okay? So after that, we've measured how long it takes for each of these to execute 2 to the 10th iterations. We get the total number of ticks for both. And then we're going to divide both of them to find out what the average number of ticks per loop iteration was. Okay? So that's what we get right over here. Okay? So we would expect that the while loop is going to take more ticks per iteration. And how many ticks do we think each iteration of that single cycle time loop is going to take? Well, by definition, a single cycle time loop is going to execute all in 1 tick. So we should see an average tick of 1 for the single cycle time loop. So let's go back to the front panel, and we've already compiled this. So I'm going to go ahead and, if we want, we can put some values here. So I'll just put 2, 2, 2, 2, 2, 2, 2, 2. Okay, and let's go ahead and run this. So this is running on the FPGA, and we've done that benchmark. Okay, so we've got our average value. So this is just the average value of this particular calculation. But what we're interested in is the benchmark values over here. So here for the while loop, we see that 2 to the 10th iterations took 7,169 ticks, and the average tick per iteration was going to be 7. Okay. If we look at our single cycle time loop, the average tick, like we thought it was going to be, is 1. Okay. So this benchmark just shows you and proves that the while loop is going to take a lot longer than the single cycle time loop in this case. Okay, let's do the discussion questions. So the first one, why does the code require more ticks in a while loop than in a single cycle time loop? So we talked about this earlier in this section. We're going to have to deal with the enable chain overhead, and also the while loop itself has a 2-cycle overhead. In a single cycle time loop, it's going to be optimized, right? And what's going to happen is all that code inside a single cycle time loop is going to execute within 1 clock tick. So what is the purpose of the decrement function on the right side of each sequence structure? So if we remember from the block diagram that we just saw, at the very end, there was a decrement function. And the purpose of that, this relates back to when we were talking about benchmarking and measuring time between events. That decrement function subtracts 1 from the result of the calculation to compensate for the execution time of the benchmarking code.